We have an insatiable demand for computation, which uses energy. Most of that computation now takes place in server farms, where we don't see it. But computing already consumes 5% of the world's electricity and is doubling every decade. All this computing is done using tiny electrical switches called transistors made of silicon. Every year the demand for computation grows by 70%. This has been mostly offset by increasing efficiency in silicon transistors due to Moore's law. However, Moore's law is ending, and the semiconductor industry has identified a need for a new, more efficient technology. A transistor uses a gate electrode to control the flow of electrons between source and drain electrodes. When electrons flow from source to drain, they run into impurities which change their direction, causing resistance and energy dissipation. Using 3 approaches, Fleet will create new types of transistors in which an electrical current can flow without resistance at room temperature. The first approach uses a topological insulator, a material which does not conduct electricity in its interior, but does conduct on its edges. These edges are one-way highways for electrons, which can travel on them without resistance. Fleet will create a topological transistor in which a gate electrode switches a material from a conventional insulator to a topological insulator. The topological edges will carry current from source to drain without resistance. The second Fleet theme will use exciton superfluids. In an exciton transistor, 2 layers of semiconductor are used. One layer contains electrons, the other holes, which are missing electrons and act as positively charged particles. The negatively charged electrons and the positively charged holes attract each other and bind together to form an exciton. Collections of excitons condense into a superfluid, which can flow without resistance. This superfluid can carry electrical currents in opposite directions in top and bottom layer. The third theme will investigate using light to create a topological state or enhance superfluidity. For example, light may be used to turn a conventional semiconductor into a topological insulator, creating a topological edge along which current can flow from source to drain. These 3 device concepts explored by Fleet have the potential for vastly lower energy consumption, transforming the future of information technology.